Good evening. Thank you for coming to my session. Today I will talk about deep dive into Kotlin Flow. I'm Jumpei Matsuda from Driver Mode, which designs and develops IBI applications for Honda motorcycles. I have been developing the multiple Android and backend applications using Kotlin Flow so far. And also, the driver mode's applications uses many flows to handle IP sheets and car signals and the states and so on. In this session, I would like to share what I learned about Kotlin Flow and the reactive streams in my experiences. By the way, if you would like to know the development of motorcycle applications, please visit the next session in Jellyfish. My boss will talk about our IB application development. Anyway, let's get to the next slide. Let's see code examples of Kotlin Flow. This code is really simple and small. It just corrects a new flow created by a built-in flow builder. If you have developed an application using Kotlin Flow, I think you can estimate the behavior of this code. 0 until 10 will be printed in the order, do something will be executed after printing 9, and then the job completes. Then how about this? An upstream has been replaced with a mutable state flow, and the default value is 0. There is no code to update the flow. This prints 0 and won't execute do something. Calling a correct function of state flow will suspend forever, as it's not a completable flow. It's an inherited behavior from shared flow, which is a supertype of state flow. Even if you don't know the inheritance relationship, Studio will show a warning like this line is not reachable. These two examples are very easy to understand and estimate. But how about the next example? The upstream has been changed again. Create a flow function whose internals are hidden, and it provides a flow instead of a mutable state flow. The signature of its return type is the flow interface. This code will print values coming from some flow instance, but we cannot know if do something will be executed or not. If this some flow instance is non-completable flow, then do something never be executed. Even when writing a small flow code, there are a lot of points you need to know and you should be able to explain. For example, when you write an incident report due to bugs of your flow code, you have to be able to give a theoretical explanation, but not just an observation. Today, I would like to help you to understand how flow-related code works, but we will not talk about getting started with flow. Topics will be flow basics, operators, operator fusion, custom operator, and testing. Let's begin from the first topic. Flow basics. Kotlin Flow is a data stream. Data streams allow us to process a single computed value from multiple asynchronous values. The flow is backed by coroutines, like a channel and a suspending function. Flow is based on the structured concurrency. And also, the flow is extensible with built-in and/or custom operators, and the custom flow classes are also allowed to create. To understand flow deeply, you need to approach it from the several key perspectives. The first perspective is the flow interface. The flow interface and its subtypes are just conventions. But Kotlin allows to downcast any subtype into the base interface. Such a flow instance hides the properties of the actual type. So please don't assume behavior based on the surface level information, like typing. It can lead to errors. The next perspective is a cold stream or hot stream. I'm going to explain a general explanation of data streams, but not limited to Kotlin Flow in this slide. A cold stream is like a faucet. The flow of water only starts when you tap the tap on. In the same way that when you call a correct function, the code in the flow executes and starts emitting values. Importantly, each corrector will get its own independent stream of values. On the other hand, a hot stream is more like a live broadcast. The broadcast is always running, and the values are always being emitted, regardless of who is correcting. Due to this property, hot streams often integrate a caching mechanism to store and share recent values with new correctors. Let's go to a cold flow slide. Flows are usually cold streams, so the code in the flow will execute when it's corrected. In this example, a lambda of a flow builder prints hello and emit words to the downstream. So each of the line 6 and 7 will print hello world. On the other hand, how about the hot flow? Hot streams are limited to Kotlin flows. For example, limited in Kotlin Flow. For example, shared flow, state flow, channels created by producing operator are hot flow. This code examples uses stating operator to transform a code flow to a hot flow. Stating internally corrects an upstream, so hello will be printed in the background due to stating operator. Even if we correct a hot flow multiple times, hello will never be printed, but only word will be printed. It means lambda over builder has executed only once. Third perspective is completable. Completable must be considered since you cannot know it until reading the internals. There is no interface indicating a completable property. And also, you shouldn't assume that whether or not completable can be judged by running the code. This code is an extreme example, but it's hard to know if a flow will need time to complete. The sample needs 1 year to complete in real time. Instead, let's rely on the fact that all flows are cancelable. Several built-in APIs like timeout can conditionally cancel to terminate the flow. Then it will be turned into the completable. Next, fourth perspective. Let's consider the perspective of the serial and the parallel executions. On downstream, you can safely use a value you receive because it's limited to a single parallelism. A downstream receives values in the order they are emitted and never processes 2 values at the same time. However, this doesn't mean it's restricted to a single thread. Number of threads depends on the used dispatcher. Okay, so then how about the upstream, so if an upstream flow runs async jobs to emit values like this example, an error will be thrown. Concurrent update is prohibited by default. If upstreams run concurrently, not necessarily in parallel, it will be rejected. You need to use flows that support concurrent emissions. For example, mutable state flow, mutable shared flow, and channel flow serialize value updates. The last perspective is backpressure. Since the machine resource is limited and the speed of value emissions are non-deterministic, the value emissions cannot be always processed immediately. You need to supply a proper backpressure strategy to an upstream. There are 4 known strategies and 1 special strategy of a mutable shell flow. First backpressure strategy is a rendezvous strategy. This is also known as an unbuffered one. This strategy suspends for at least 1 corrector to be ready before emitting the next value. This doesn't require an extra buffer, but not suitable for time-sensitive value emissions, as it may spend time due to suspension. Conflict strategy is popular as a state flow uses this strategy. It may drop values if a workload is high, but the most recent value will be surely sent to a downstream. This can mitigate a burst value emission, but a slow corrector would lose intermediate values instead. If you need all values, this is not an option. Third backpressure strategy is a limited buffer. It stores values in a buffer and processes them later. A corrector can receive all values while a buffer has a remaining capacity. Otherwise, the overflow still happens. And also, the larger capacity will increase memory consumption. So please be careful when you use a limited buffer strategy. Another variant of buffer strategy, buffer, is unlimited one. A corrector will receive all values, but burst value emissions may, the burst emission will cause out-of-memory errors. So you can use this strategy when you know the length, or you can accept such a long buffer. Last one is a mutable shared flow special strategy. This conditionally selects a strategy depending on the number of correctors. If at least 1 corrector exists, it uses limited buffer strategy. Otherwise, it will dismiss value emissions. Next topic is flow builders, operators, and operator fusion. Flow APIs consist of the builders and the operators APIs. The builder APIs produce a flow instance by purpose, and operators will return a new transformed flow or transform received values into some representation like list, for example. So I would like to pick up 4 common flow builders. First, the flow function that takes a lambda is the simplest builder. It produces a cold flow satisfying the minimum requirements of flow, and parallel value emissions are not supported by this builder. Channel flow supports parallel value updates. For example, since a callback would be called from another thread, channel flow is helpful for such a case. Actually, you may know callback flow function. Callback flow function is a minor modification of channel flow, actually. And also, coroutine scope is available as a receiver, so you can handle multiple asynchronously computed values by channel flow. Third builder is the mutable shared flow. It's very famous, right? This produces a hot flow and supports serialization. This can enable cache to share values between downstreams. And also, you can purge cache anytime. This has a conditional backpressure with depending on number of characters, as I said. So I recommend to use subscription count property to observe character size changes. Last builder is the mutable state flow. This is also a very popular builder. You can read and write the last value through thread-safe APIs. It has atomic references for APIs, like compare and set function. And it allows to achieve the serialized UI state management, for example. As this conflates values, don't need to care about burst updates. Let me drink a water. Next topic is flow operators. There are a lot of operators to transform a flow. Operators are categorized by intermediate operators and terminal operators. Intermediate operator is like working like registering the lazy effect to an upstream. It doesn't execute any code in the flow until it's corrected. Some intermediate operators can produce a conditionally completable completable flow, even from a non-completable flow. A terminal operator starts correcting a flow and produce computed values. An operator to create a hot flow like stating is also a terminal operator, as it causes the side effect to an upstream when it's called. Most of terminal operators require completable, so please consider using intermediate operator to ensure you get a completable flow if required. Operator fusion. I will talk about operator fusion. The operator fusion is often shown in the KDocs. I'm not sure if that there is a same terminology in the compiler optimization about Lambda or something, but in this slide, operator fusion means like what the Flow API designs. First, the no terminal operator is fusible. Operator fusion is currently designed only for intermediate operators. If you were guessing that an operator fusion is what Sequence API does, then it's not correct. A non-fusible operator builds a new flow wrapping an upstream. Unlike that, a fusible operator avoids creating a redundant wrapper. For example, flow operator wraps an upstream by a channel flow operator implementation class. But when you call flow for a channel flow operator implementation class itself, it doesn't create a wrapped channel flow operator imp, but a fuse dispatcher configuration instead. And also the number of the fusible operators are not so many. Operator fusion would decrease the overhead compared to the redundantly wrapped flows, but it's actually required to avoid running a flow on old context and old backpressure. If our flow runs on such an old configuration, results may differ because the buffer overflow may happen if an old configuration has a smaller buffer size, for example. Okay, so let's go to the customization section. So for customization, of course, we can create a custom flow builders and the custom operators by using built-in flow APIs. I picked up 3 options, but didn't include mutable state flow and the mutable shared flow because they are not easily extensible and have special behaviors. Honestly speaking, I haven't seen any use case that requires the mutable state flow or mutable shared flow for custom operator. And I think these 3 options are good enough. This chart shows how to choose a proper flow builder. If you require stateful flow, please create a class extending abstract flow class. Don't extend the flow interface directly. Extending the abstract flow class satisfies the pre-requirements of the flow convention, like cancelable, context preservation, and exception transparency. I will not explain context preservation and exception transparency, but don't need to care about that if you follow this chart. When you'd like to aggregate multiple concurrent values, you need to use channel flow that shares the value emissions. And it will be like, stateless flow. Otherwise, please use a flow function that takes a lambda. It's the simplest builder. It's good enough and the best performance for many use cases if you don't need to support concurrent updates and state. From my experiences, these 5 operators could cover the point of advanced custom operators and or finding a solution of mysterious bugs in flow. You should check the internal implementations of running flow, transform latest, sample, merge, and statewing or sharing. Running for the operator can fold on upstream and return the intermediate results as a flow. The code holds a previous result and compute a new result by using it and the latest value from upstream. This processing is guaranteed to be a single concurrency, so no external synchronization is required. And this doesn't need to use channel flow. Transform latest internally cancels the previous ongoing transformation when an upstream emits a new value. This operator shows that you can safely use coroutine scope function, launch, and cancel jobs if it's a custom flow class. Using channel flow is also fine if it's stateless. Third operator is a sample function. This API is marked as experimental, but you can use this operator for throttling, so burst control. You can learn how to use select API to handle multiple value sources concurrently from this operator. I'm not going to explain the details, but remark points for those who would like to read the implementation later. First, sample function creates a channel to collect values from an upstream. Secondly, a time ticker will be created as a secondary source. So this handles 2 value sources. After preparing the sources, the sample uses select API to wait for first come value from these multiple suspending functions. When an upstream emits a value, sample holds it and wait for next value from the two sources again. When a ticker fires first, sample emits the holded latest value of an upstream to a downstream. Sample uses the custom time ticker as a secondary source. So, of course, you can use any other flow and or two or more sources in the same way. Built-in combine and or zip operators use a different way to orchestrate multiple flows, but it's difficult to imitate, honestly. So I prefer this way for concurrent sources. First operator is stating and or sharing. These operators turn cold flow into hot flow. Both internals are very similar, so I would like to explain only stating. Both launch a value sharing job, which collects an upstream in the background. So collected values will be sent to a returned returned flow in the background. The last operator is a merge operator. This flattens the collection of flow into one flow, but this shows that we need to be careful about when to correct upstreams. Each upstream will be corrected in background job, so such operations may not work well with zero reply mutable shared flow. Let's say you have a class that that encapsulates a mutable state flow and its subscription count property is not accessible from externally, then it may accidentally dismiss values due to a race condition, and the core has nothing to do at the time. So it causes like a mysterious bug. So the last topic of my presentation is about testing flows. I would like to share my testing strategy for each of custom operator testing and cross-using flow. Honestly speaking, I'm still looking for a better practice, but hope that this could be your help. As for the common coroutine debugging, please check out my last year's session. I believe it would be useful when writing test code. First, I strongly recommend to introduce tabbing, which is a very useful assertion library for flow testing developed by a cache app. I really recommend, but it's not only for the convenience perspective. So first, the mutable state flow won't properly work for many testing. It's conflated and distinct, so some intermediate values may not be assertable. How about the mutable shared flow? If you write a correct testing by using a mutable shared flow as a downstream, the right code in this slide is required, for example, and I know you don't like to write this template every time, so I can't say the difference is so small. Even if you use a channel class, required code will be big. That's why I'd like to recommend tabbing. I always use tabbing for both custom operator testing and when testing a cross-using flow. As for custom operator testing, I have a test template. So in my test template, the upstream is always an unlimited buffer channel. This can provide a pure data stream, which doesn't conflate values and doesn't remove any duplicated values, unlike mutable state flow. Unlimited channel is not completable by default. So I use either type to emulate the completion. I tend to use a left object to perform the successful completion or throw an exception. If a custom operator takes a coroutine scope, don't pass test scope, but use background scope or custom scope. You can manage. Test scope is very popular for coroutine testing, and I often use it, of course. But it's not always good for flow testing. Run test function internally waits the completion of the test scope's job, but it won't complete if at least one job is running. So in a custom operator launches a job internally and the upstream is not completable, then the new job keep running. So run test will always close timeout. Instead, the background scope or managed scope is a good fit. Unlike test scope, the running jobs in background scope will be canceled when the test body finishes. As for managed scope, please cancel it by yourself. Lastly, assert a new flow by using tabbing and the channel APIs. We can perform the value emissions, assertions, cancellation, and completion on demand by this test template. So this is the final section. Let's see how to test across using flow. So I'm sorry, but I don't have a test template for this case. So I would like to share the few tips from my experiences. This may feel strange if we were used to abstraction with interfaces, but it would be better to use the same flow builder for both the production implementation and the test class whenever possible. Especially when a class has both the read and write APIs through a flow instance, like this code is example code, the implementation difference would produce long test. For example, mutable state flow accepts values even if it has no character, but unlike mutable shared flow drops the values. Next tip is last topic. I recommend to use multi-threaded dispatcher for flow testing. When you use a test scope, the default dispatcher will be instance of a test coroutine dispatcher. It uses the virtual time source and replace delay implementation to use the virtual clock. Generally speaking, this is useful when writing the coroutine testing. However, it will hide race conditions due to single concurrency, as test coroutine dispatcher is a single-threaded dispatcher. For reliable testing, the multi-threaded behavior should be tested. Since you can adjust the virtual clock in foreground code, background jobs don't need to have a test coroutine dispatcher. Instead, we should inject a time source class. Use test time source instance during testing, which can be retrieved from the test scope instance, and adjust the virtual clock only from the foreground code. Okay, let's set up a procession. The flow is a stream, and its API designed to transform concurrency into a single parallelism downstream. And in this session, I shared the 5 key perspectives of flow and the 5 operators for running flow more. And also, I shared several tips for flow testing, like a test template for custom operators. That's it. Let's write a safe flow code. Thank you for listening.